Okay, Assalamualaikum and good morning. So today I would like to share with you our final slide for this course MEMM 1313. So this is the final tutorial for chapter 6. It is about the the turbulent boundary layer. So we go for this question first. Determine the shape vector h if the velocity profile is u over u equal eta by the power of 1 over 6. So in this question, we need to calculate the shape vector h here, okay, when the velocity profile is given by u over u is equal to eta to the power of 1 over 6. In normal calculation, we could write boundary layer velocity profile as u over capital U equal to y over delta. But if we see notes from Blasius, how they do the Blasius exact solution, because there is a lot of component. So to simplify the equation, they will compile all the unknown parameter into an eta here. That's why in some boundary layer solution, they will write the velocity profile as eta with the power of something like this. Okay, so and then it is depend on you whether you want to solve a turbulent boundary layer in terms of eta or in terms of y and delta, like this one. Both will give you a correct answer. Okay, so shape vector can be determined as delta star over theta. That's why in the beginning of boundary layer lesson, I already introduced you the equation for delta star and theta. So and then on that time, I introduced you the equation for delta star as shown here, which is the integration 1 minus u over u dy. So in this equation, you need to substitute the velocity profile here, u over u, in terms of y over delta, because the integration is 2 dy here. But if you want to use the eta like this, you need to use the equation of this one. Means the equation will become integration of 1 minus f eta delta and d eta. Because the integration is to d eta, that means we could use the velocity profile in terms of eta in this equation. So and then this is the equation for theta. So we have equation integration of dy or the integration of d eta. And then another thing that you need to understand is if you use the integration equation of dy like this one, the integration limit is from 0 to delta. However, if you use equation of eta here, the integration limit is from 0 to 1. So please be careful when you choose equation to solve delta star and theta. So and then if we calculate the value of delta star, we substitute the value of f eta. So it is eta to the power 1 over 6. So we will get 1 over 7 delta. And the theta here will give us 3 over 28 delta. And then we could calculate the value of h here is the ratio between delta star over theta. And then we get the value is 1.333. A shape vector is used in boundary layer flow to determine the nature of the flow. The higher the value of h, the stronger the adverse pressure gradient. A high adverse pressure gradient can greatly reduce the Reynolds number at which transition into turbulence may occur. So the idea is by having the value of H, we could determine whether it is laminar boundary layer or turbulent boundary layer. Okay, so conventionally, H equal 2.59 is typical of laminar flow, and then if H equal 1.3 to 1.4, it is a typical of turbulent flow. So means that by looking the ratio, the shape factor, so the ratio of delta star and theta, we could predict whether the boundary layer is in laminar or in turbulent. Then we try to solve this problem. For example, we have a flat plate like this. Water at 20 degrees Celsius and 1 atm flows at 6 meter per second past a smooth flat plate, 1 meter long and 60 centimeter wide. Take the Reynolds critical is 10 to the power of 6. And then we need to estimate the trailing edge boundary layer thickness, the trailing edge wall shear stress, and the drag of one side of the plate. So in this question, we have a flat plate and it is a smooth plate. So this is the dimension, 1 meter long and 60 meter wide. And then we know the transition Reynolds number means the transition means the condition where laminar boundary layer will become turbulent boundary layer. And then this is the question that we need to solve. Okay, first we need to calculate the Reynolds number at the edge of the plate. So from the calculation, we substitute the value of x, which is 1 meter. So we get it is 5.9 times 10 to the power of 6. So and then we compare with the Reynolds critical here. So we could determine that this Reynolds number is a fully turbulent boundary layer. So and then we need to determine whether the laminar boundary layer is need to be counted or not. So because the transition Reynolds number is given in the question, so we use the transition Reynolds number here and we do reverse calculation. So this is the Reynolds number equation. So we left the amount of x here as unknown, and then we could find that the value of x is 0.167 meter. So and then if we make some simple analysis, we found that this 0.167 meter is around 16% from the total length of flat plate. So because it is exceeding 10%, so we assume that the effect of laminar boundary layer cannot be ignored. So what we need to do is actually, we need to calculate both. We need to include the effect of laminar boundary layer in our next calculation. Okay, next step, we need to determine what is the boundary layer thickness in laminar boundary layer. So, and then we know that the Reynolds transition is 10 to the power of 6. So this is the equation for boundary layer thickness according to the Blasius-Isaac solution. Because in this question, we don't know the velocity profile for laminar and turbulent. And then because we don't know the velocity profile, we can solve problems for laminar boundary layer by using Blasius-Isaac solution, and then we could use 1/7 power law to solve problem of turbulent boundary layer. So this equation is from Blasius-Isaac solution. It is 5x over square root Reynolds. So we substitute the critical Reynolds number. So and then we substitute the value of x, which is the distance of laminar boundary layer only, which is 0.167 meter, and then we could get the boundary layer thickness as 0.000835 meter. So this value is actually the boundary layer thickness at this location, at this point. So and then the turbulent boundary layer here, okay, it will become like this. So and then, okay, it means that this thickness also shared by the turbulent boundary layer, so that we could calculate the distance of x here, the distance of this one, okay, by using the thickness of this boundary layer. So the calculation will become like this. So this equation is actually comes from the 1/7 power law. Okay, we substitute the value of delta and then we could calculate the value of x here. So the value of x is equal to 0.03557 meter. So means that so the distance of the boundary layer from its original point here is equal to 0.3 as this one, 0.355 meter. And then we could determine what is the total length of turbulent boundary layer only by using this equation. So we could get that the x for turbulent is equal to 0.86857 meters. Then we could calculate the trailing edge boundary layer thickness by using the turbulent boundary layer thickness equation. So here I hope you could understand that we have a flat plate, we have a laminar, and then we have a turbulent like this one. So and then to calculate the boundary layer thickness at the end here, okay, we are using turbulent boundary layer equation because this is turbulent boundary layer equation. But the most important things that you need to know is we need to use the distance from here to here only, because this is the starting point for the turbulent boundary layer and this is the end point of turbulent boundary layer. That's why in previous calculation we need to calculate the value of x turbulent, because we need to know what is the total length of turbulent boundary layer only. So and then we substitute into this x. So we found that it is equal to 0.01466 meter. So means that this boundary layer thickness is equal to 0.01466 meter. And then we can calculate the trailing edge wall shear stress. So means that we need to calculate what is the shear stress at the end of this plate. Okay, you need to understand that the shear stress is, the unit for shear stress is Pascal. So means that it is some kind equal of pressure. So means that the shear stress here is the shear stress value at this point only, at the last point of this flat plate. So because in this point, on this, okay, in this point, it is a turbulent boundary layer. So we could use the equation for 1/7 power law, and then we substitute the Reynolds number here. And then please be careful, the Reynolds number here is actually the Reynolds number based on this distance, mean based on the total distance of turbulent boundary layer only. So and then if we substitute the Reynolds number here, we could get that the shear stress at the end of the flat plate here is equal to 47.11 Pascal. So and then we need to calculate the drag force of one side of the plate. So here, I hope you still remember, because we have laminar and then we have a turbulent here. We cannot just use equation for turbulent boundary layer, because we need to calculate the total drag force on the flat plate. So means we need to calculate force due to the laminar boundary layer, and then we need to add with the force due to the turbulent boundary layer here. So some students will confuse with the idea of shear stress. So for idea of shear stress, we are only calculating the shear stress at this point only. That's why we could use equation for turbulent boundary layer, because we are calculating shear stress at this point only. Okay, but for drag force here, you need to calculate all the uh, things that give force on the flat plate. And then, according to the notes, okay, I give you previously, we have a table like this. You need to check what is your Reynolds critical, and then you could choose equation to calculate the drag force, drag coefficient. However, in our question here, our Reynolds critical is 10 to the power of 6, which is not in this table. So what we could do is we could make an interpolation calculation. So this is, we plot the Reynolds number of this one, the critical Reynolds number, and the value of this constant. So, and then we could have this line, and then we could have some kind of equation to build the relation between these three points. So we could have this equation, and then we could predict what is the value of CD if the Reynolds critical is 10 to the power of 6. So we just substitute the value of X here with 10 to the power of 6. So, and then we could get the value of Y, and then it is almost equal to 4,000. So by using this equation, we could calculate the drag force for the total plate. So the CD is 0.002552. So, and then we could calculate the drag force for only one side here as 27.51 Newton. And then we continue our discussion here with same phenomenon, with same condition, which is water at 20 degree, 180 m, flows at 6 meter per second, and Reynolds critical is assumed to be almost 10 to the power of 6. So this is the dimension 1 meter long and 60 meter wide. But we are not using a smooth flat plate. We are now using a rough flat plate with average roughness of 0.1 millimeter. So here I hope you could understand that the parameter of surface roughness, sometimes you are using RA, sometimes you are using RV or RP and so on. So the unit for surface roughness is actually length, because I hope you could make some revision how surface roughness being calculated. So it is actually the calculation of area of the hill and the area of the valley on the surface topography. Okay, so in this situation, we are assumed that we create an artificial roughness on the surface. So for example, we put a sandpaper on a flat plate, then we do the experimental works like this one. And then we need to estimate these three items, same with the previous question: the trailing edge boundary layer thickness, the trailing edge wall shear stress, and the drag of one side of the plate. So again, we check the Reynolds number, because the Reynolds number is not influenced by the surface roughness. So as you know, the equation for Reynolds number is rho ux over mu. So means that the surface roughness is not change the Reynolds number. So this is the Reynolds number, same as previous question. And then we have a roughness height, means a parameter that need to reflect the surface roughness on the flat plate. So because it is 0.1 millimeter, so we write as K is equal 0.0001 meter. So and then I would like to introduce you one equation, a few ideas actually, to calculate the drag force, the boundary layer thickness, if our flat plate is not smooth. So we are not discussing the idea, the derivation of the equation, because it is not the syllabus, and then the derivation of this equation is actually not comes from mathematics solution only. It is actually based on the experimental value and then a curve fitting. So means that previous researcher, they are doing a lot of experiments using a rough flat plate. They plot in so many graphs, and then they try to get the very best correlation, and then they start to use that equation to solve problems without doing the experimental works. So that is the idea. You could read from the textbook, but in this syllabus, I would like to only show you only two methods to calculate the drag force and so on by using equation. At least we have a two equation here. Okay, you could refer our textbook from equation 682. We have this Reynolds number equation. So Rex here. So the Reynolds number is equal to as shown in this slide. So and then we have some simplification. For example, the value of Z here is K lambda, which is the K here is the Kalman constant. Normally we are using 0.41. So and then the lambda here is actually the second viscosity coefficient, and the correlation of lambda and local drag coefficient CF can be written as this one, 2 over CF to the power of 1 over 2, means the square root of 2 over CF. So and then we have a K plus here in this equation. So we have a K plus, and K plus here is actually the sand grain roughness coefficient. So as I said, normally they use a sandpaper to start the experimental work of this one, and then they start to give some kind of coefficient for this sandpaper. So we call it as a sand grain roughness coefficient, and then it can be equal with K V star over nu, and nu here is the kinematic viscosity of the fluid. And then another equation related of this one, we could write the K plus here is equal to Reynolds number K over X over lambda. And then we have an EZ here. So the equation, we have an EZ here. So the EZ here is the exponent to the power of Z. So and then the Z is actually this term. So the exponent is 2.718. Okay, so we could substitute into this one. So if we see this equation, we could substitute all the value. We could substitute the value at K plus. We could substitute the EZ. And then we have the Z here. We could substitute the K plus here. And then this is the Z. And then we found that the right hand side will give us the only unknown parameter, which is lambda. So if we substitute the Z, we have lambda here. So and then if we substitute K plus, we have a lambda here. So and then we have the EZ, and then this Z is also have lambda. So means that the only unknown parameter in this equation is lambda. So and then if we do the try and error method, or you solve it with MATLAB and so on, you could get the value of lambda is almost 22.07. So and then from that value, lambda equal 22.07, we are substituting into this equation. We have u over v star, and then we substitute the u here with the free stream velocity, which is 6 meter per second. So we get the v star here is 0.272 meter per second. So and then we could calculate the value of k plus like this. So and then we could get it is equal to 27.14. So this is the kinematic value, kinematic viscosity value. So it's depend on you whether you want to use the kinematic viscosity, because the relationship here is mu is equal rho nu. So if nu is equal to mu over rho, so that here is the value of mu over rho. Okay, so please do not misunderstanding the calculation here. Okay, so and then after we calculating of all the things here, okay, we need to solve the idea of delta B. So delta B is given by this equation. So and then if we substitute everything, we could get the delta B is equal to 5.397 meter. Okay, after that we need to solve this equation. So we have a lambda which is equal to 1 over k ln delta v star over nu plus b minus delta b. So the unknown here is the delta, which is the boundary layer thickness. So and then if we substitute all the value we get, the b here is constant as 5.0. Okay, so and then we could get the delta is equal to 0.03688 meter. So if we compare with the result from smooth flat plate, we found that on smooth flat plate here, so the delta is smaller compared to what we have on rough plate. So mean that this calculation is quite is irrelevant with the common idea about the formation of boundary layer on smooth and rough surface. You could imagine on rough surface the turbulent boundary layer maybe occur earlier. So and then the boundary layer thickness will become thicker. So and then we could calculate the trailing edge wall shear stress. We could calculate by using this equation. So we could get it is equal to 73.84 Pascal. So and then we also could calculate the shear stress by calculating this one. So we know that lambda is 22.07 and it is equal to square root 2 over CF. And then we get the value of CF is 0.004161. So and then we could get the Pascal is 73.76 Pascal. So the difference here is quite small. So we have only 0. Okay, this is less than 0.1. Okay, so means that both calculation can be used to solve this problem. So and then we could calculate the drag force for one side of the plate. We could use this equation. Okay, CD is equal to 1.15 CF. So and then we could get CD is 0.004722. So we could calculate the drag force here as CD times 1 over 2 rho AU square, which is equal to 50.9 Newton. Also, and then if you read the textbook, it is hard to determine or hard to define about roughness, whether it is fully rough or it is the intermediate rough and so on and so forth. Okay, if the surface is rough, okay, another estimation of CD can be done by using this equation. Okay, so and then we substitute all the data here. So the L here is the length of the plate, and the K here is the surface roughness index. So means the surface roughness value. So and then we could get the CD is equal of 0.004934. So if you see the comparison of this one, so it is 4722. So here is 4934. So we have a little bit large, greater number here. So and then we could calculate the drag force here as 53.18 Newton. So and then it is actually how to determine whether our drag force is correct or not. So it's depend on the roughness of the surface, because it is hard actually. That's why in turbulent boundary layer, normally people will compare with the experimental value, because the turbulent flow is actually still unpredictable. Maybe your sand is not so rough, but it maybe create a very bad turbulent flow. So and then because of that, we need to check whether our flow, our roughness is fully roughness or intermediate roughness. So if you want, so it's depend on the research or on the equation that you want to use. For example, if you want to use this equation, okay, normally you need to check whether it is rough or not by using this method. So we need to check the Reynolds number by using the K, means we call it as Reynolds number K. So the equation is like this: rho UK of mu instead of rho UX of mu over mu. So we substitute the value here as the value of the roughness, and then we get it is 599. So the condition if the Reynolds number is more than 1200, so we could assume it is fully rough. So when it is fully rough, we need to use this equation normally. So but the condition here is less than 1200, so it is okay for you to use this equation. Okay. However, this is just the estimation because the turbulent condition is actually need to be verified later on with the experimental value. So and then I would like to share with you another method, a simple one, to calculate the drag force and boundary layer thickness on a rough surface. So let's say we still have the same condition like this one. Okay, so and then please ignore of the Reynolds transition here. We have there is a typo there. The Reynolds transition. Okay, so first we need to calculate the Reynolds number, as I said, so that we still have the same amount of Reynolds number, which is 5.9 times 10 to the power of 6. So now, if you want to use this simple calculation, you need to check whether it is rough condition or not. So the idea is very simple. We just check the value of x over k. So the length is 1 and the surface roughness is 0.0001. So we get it is equal to 10,000. And then we compare with the value of Reynolds number over 1000. So because the Reynolds number is 5.988000, so it will give us almost 6,000. So 10,000 is greater than 6,000. So we could assume that this condition is actually fully rough condition. So for this situation, we could calculate the value of CF by using this equation. So we get the CF is equal to 0.00381. So and then from the CF there, we could calculate the value of lambda. And then from the value of lambda, we could calculate the value of U over V star. So and then the V star is equal to 0.262 meter per second. And then after we get the value of V star here, we could calculate the value of K plus, which is equal to 26.1476. And then we could use the equation of delta B. So here the equation of delta B is still the same equation as shown in previous solution. So however, the way we could determine the idea of CF is quite easy compared to the previous method. So here we get the delta B here is equal 5.3165. So and then we substitute in this equation, we could get the value of C delta here, which is 0.0523 meter. So and then here the amount of CD is actually a little bit larger compared to the previous calculation. So here we get 0.0523 meter, but from the previous calculation we get it is around 0.03 meter. So and then we also could calculate the value of CD, and finally we could get the value of FD by using this equation. Okay, so by using this equation. Okay, so here we substitute everything, so we could get it's almost something like this, because this is the correlation is quite good, so we could assume that for rough condition, so the value of CD can be estimated by using this equation.